عرفت ليش كذا كنت أول ما كنت في وداع في اللغة مراجعة.
Gentlemen, everything that we will cover up to the end of today's class will be covered in the major exam. Anything we cover after today's class will not be tested in major 1, will be tested in major 2. Or for major 2, anything we cover after today will be covered in major 2. Yes. Today included.
What do you suggest?
Yeah, notes. If the notes are clear to you, I don't think there is need to refer to the book. The notes are prepared from the book. But if you feel any confusion in any point, you can refer back to the book. The book will give you more details. And if you're still not able to understand, come back to me. I will explain it to you. I uploaded a list of questions, like 4 or 5 questions from each chapter. If you are able to perform those, I don't think there is anything else needed.
The question in the
Yes.
enough or
Yeah, they are more than enough. Okay, I want you to turn off your mobiles and look at the screen for your full name. Ahmed Abbas. Binder Sultan. Ahmad Mustafa. Ahmad Ahmed. Hussein Jafar. Saud Fahad. Abdullah Suleiman. Saud Abdul Aziz. Salman Fahad. Ahmad Ahmed. Ahmad Ahmed. Salman Abdullah.
Yes.
Faisal Fahad. Ahmad Abdullah. Fahad Khalid. Fahad Khalid. Abdurrahman Adil. Ahmad Suleiman. Ahmad Ahmed. Hamid. Ahmad Haytham. Hadib Farooq. Ibrahim.
Yes.
Yusuf.
Yes.
Hussein. Hassan Ahmed. Abdul Hadi. Ahmed. Jawad.
Yes.
Yes.
Ahmed Abdul Aziz.
Yes.
Ahmed Assam.
Yes.
Mishal.
Yes.
Saad. Fahad Saeed.
Yes.
Abdul Aziz Abdurrahman. Anyone who came during the attendance? No one? Of course, yes. In the whole class, we are not doing this thing for fun. It will be tested. Now, I will repeat the whole thing that we did in the previous week. And from there, I will kick on and extend this testing of one coefficient, testing of all coefficients. And the next topic is what? Testing of some coefficients using partial F test. Today, I will try to discuss the partial F test for testing the significance of some coefficients. So you see, we started the week 6 with defining a multiple linear regression model in scalar form. This was the model, and we said this should be the procedure of estimating the model using OLS estimation. We have k+1 unknowns, k+1 equations. But the estimation becomes easy if we define this model in terms of matrices. We did that in terms of the model at the top, where we defined the beta vector to be this, y matrix was defined, x matrix was defined, y vector was defined, epsilon was defined. Then we said that the estimator for this beta is beta hat, where beta hat is x transpose x whole inverse times x transpose y. This formula came using the method of least squares. We got this formula using the method of least squares. This beta hat, we know it will be a column. And in this column, how many values will be there? K plus 1 values will be there. So you will read this column like the first value is the intercept, the second value is beta 1 hat, the third value is beta 2 hat, and so on. Then if you multiply this beta hat, pre-multiply this beta hat with the X matrix, you get the Y hats. You can get the Y hats like this one, or you can get the Y hats if you want using the basic scalar form of the model. That means you extract those beta hats from the vector and put them back into the equation and multiply one by one to get Y hats. It's up to you if you want to do it in one command or you want to do it with that drag down option of Excel. Anyways, you can use that method or you can use this method to get Y hats. These two methods are both okay. They will give you same Y hats. Once you have the estimated values, you can get the residuals. The residuals are nothing but the differences between the actual Y's and Y hats. Where will these residuals help you? They will help you in getting MSE. And MSE is used in almost every single inference we perform, every single hypothesis test we perform. Yes. Then we kept repeating the same thing, and then we had a little derivation to show that these beta hats, all of them, they are unbiased for beta. And their variance covariance matrix was found out to be a k plus 1 by k plus 1 matrix. But the problem with this one is there is an unknown parameter in this derivation, which is sigma square. We need an estimate of this sigma square. To get to the estimate of this sigma square, we find SSE and we divide it by n minus k minus 1, and this gives us MSE. This is the estimate for sigma square. You plug this back into this one, and the resulting variance covariances will be the estimated variance covariances. So you put a big hat over this one. If you replace sigma square by MSE, the variance covariances will be the estimated variance covariances, which I'm using there in the T statistic if you see. So the critical point of hypothesis testing is to get to SSE, and to get to SSE, you need the ease, and to get ease, you need the model. So it's step by step. Then we started discussing the 4 hypothesis tests that we will cover in this chapter. Testing a single slope, we discussed it using the t-test. We can test a single slope. We can test upper-sided, lower-sided, two-sided, any hypothesis about a single coefficient using the t-test. Then last class, we discussed the logic behind the F-test, full F-test for testing the whole model. We did develop this full F-test, and we also discussed and did not prove that this test statistic follows an F distribution with V1 and V2 degrees of freedom, where V1 is the number of predictors, V2 is n minus k minus 1. We also wrote down the rejection region approach and also the p-value expression for this test. And this is where we stopped. Now, in today's class, what we are going to discuss is what if we are interested in testing some coefficients of the model. For example, ultimate name of this test will be a partial F test. So today we are going to discuss this. Any question from the previous week? No question. Okay, so let us assume I'm going to write an imaginary model. Let us assume that this is the model we are working with. So in this model, how many predictors do I have? 4 predictors. X1, X2, X3, X4, 4 predictors. So how many unknown parameters do I have? I have 5 plus 1. Which one is plus 1? Sigma square. Inside error, there is sigma square. So I have 5 plus 1 parameters there. I have actually 6 parameters. 4 slopes, 1 intercept, and 1 variance. 4 slopes, 1 intercept, and 1 variance. So let us say from this model, I'm interested in testing H naught that beta 2 and beta 3 are 0. I want to test this portion of the model against H1 that at least 1 beta j is not equal to 0 for all j equals 2 and 3. Either beta 2 is not 0 or beta 3 is not 0. Suppose this is what I want to test. This is not one predictor, unlike the t-test. This is not all predictors, unlike the full f-test. This is some predictors. Now to test, yes, for all. It's the notation for all. For all j equals 2 and 3. Now for testing this thing, what you need to see is that in the presence of x1 and x4, that's the objective of the test. We want to test that in the presence of x1 and x4, do x2 and 3 contribute significantly? That's the question you are asking in this hypothesis. This is the spirit of the hypothesis. Again, the spirit of this hypothesis is to test that in presence of x1 and x4 in the model, are x2 and x3 really needed? Are they contributing significantly in predicting y in the presence of x1 and x4? We need to answer this question. To answer this question, we need to see the marginal contribution of x2 and x3 in the presence of x1 and x4. And for that, at the end of the last class, we introduced a term that is called extra sum of square. What is this extra sum of square? This extra sum of square tells you the sum of squares increased by one or more than one predictors in the presence of other predictors. So if you really want to see the marginal contribution of x2 and x3 in the presence of x1 and x4, you need to fit two models. Every time you are using a partial F test, you need to do this. Fit two models. Which two models? Full model and let's call it revised model. Your full model will be this model. Let me copy it as it is. This will be the full model. And your revised model will be without the two variables that you are testing in H node. It will be beta naught plus beta 1 x1 plus beta 4 x4 plus epsilon. So fit these two models. Make separate X metrics for the model 1, separate X metrics for model 2, and all that. Excel can do it directly for you also. We'll use the direct option of Excel. Today, I'll tell you how to get the model and the summary of the model directly from Excel. So we will fit these two models. Now, what we are going to do, we are going to get SSR from the first model. What will this tell us? This will tell us variation in y explained by x1, x2, x3, and x4, the four predictors, correct? Then I will obtain SSR from revised model. This will tell me the variation in y explained by x1, and x4 only. True. And what if I take the difference of the two? This will give me, let me denote it by SSR of x2 and x3 given x1 and x4. This will tell me the marginal contribution in y explained by x2 and x3, comma, in the presence of x1 and x4. So this extra sum of square will tell me the marginal contribution of x2 and x3, which I'm interested in, which I am interested in for testing this hypothesis. Now, one of the arguments can be, if you want to devise F statistic for checking whether x2 and x3 are contributing significantly or not, you can simply define F statistic as SSR from the regression, this regression, SSR from this regression, over 2 over SSE over n minus k minus 1. Why we are bringing x1 and x4 into the picture? You can just simply fit one model with x2 and x3, take SSR from there. That will be the contribution of x2 and x3 for explaining the variation in y. Why don't we do that? It's a completely different thing. We want to see the contribution of x2 and x3, not the absolute contribution. We want to see the contribution of x2, x3 in the presence of other predictors. So this is actually the contribution of x2 and x3. If you just fit a regression of y on x2 and x3 and get SSR, that will be the contribution of x2, x3 in explaining y, but not in the presence of x1 and x2. It will be absolute contribution, and we are not interested in that. We are interested in this. Given x1 and x4. This is the baseline for your testing. What if this value is 0? What will be the conclusion? No contribution by x2 and x3 in the presence of x1 and x4. What should you conclude? Go back to h0, h1. If there is no contribution, that means you should be accepting h0. You should be going with h0. So a value of that thing, SSR, the extra sum of square, close to 0, means you should be accepting h0. Yes.
When we test more than one variable, maybe the first variable is not equal to 0, but the other one is equal to 0. How can we know that?
Again, when you are testing the two variables, why it's not changing? I'll explain what it here. When you are testing the two variables x2 and x3, your question is that in case this one is 0 and this one is not 0, what will happen? Of course, you will reject h0. Yes. Because your h1 says anyone, at least one, either this one or both. So if any one of them is contributing significantly, you will be rejecting h0. So what will happen if this thing is close to 0? This thing is close to 0. You go with h0. What if this is close to infinity? Or let's say I say SST. You will be rejecting h0 because they are contributing significantly. If this is a big number, that means the contribution is big.
This is close to 0. How close?
If it is close to 0, yes, that's the question. How close to 0? Now, to see how close to 0, you need to see this thing in the relative terms. Relative to what? Relative to unexplained variation. And you cannot compare the sums, correct? Exactly the same spirit that we implemented here. You cannot compare the sums. You cannot take the ratios of the sums. So you converted the sums to means by dividing the number from where that sum is coming. So this is SSR of how many predictors? Two predictors. So I will divide it by the number of predictors it is coming from. What is R? In general. The number of predictors?
And the formula minus the number predictor and the y.
No.
Y is what?
Luckily, in this example, they are equal, but now. No, it is the number of predictors you are testing in H0. How many are you testing in H0? You are testing 2 here. Luckily, this 2 is equal to this 2, but because we had 4 predictors total, so luckily this 2 is equal to that 2, but you will not get it from the revised model. You will get it from H0. You will get it from H0. How many predictors are contributing to this one? That's the right answer, R. So I denote it by R. R is the number of restrictions I'm putting onto the model. How many restrictions am I putting onto the model? 2 restrictions. One, beta 2 is 0. Second, beta 3 is 0. So I will divide it by R, and the denominator as it is, I'll divide it by. The denominator is basically the MSE of the full model. So you compare the marginal contribution of X2 and X3 with MSE of the full model, and this gives you an F statistic. And the same spirit, yes. You can do that also. You can find the extra sum of squares from that formula also. You mean in the denominator? No, in the denominator, you compare it with the total variation explained. The overall variation explained. Now, this F statistic will stay between 0 and infinity, where 0 indicates what? And infinity indicates H1. So you will reject H0 if F is big. How big? From the tabular value. And you can also define the p-value expression. Like this. Now, the good thing about this partial F test is that this is a generalized form of both of these two. Because sum can be 1. I mean, this sum, not SUM. This test is developed for testing some predictors, correct? That sum can be 1. So it is an alternative to that t-test. You can use this procedure to test that one. And sum can be all. So you can also use this procedure to test the significance of whole model. So this is the most generalized, not the most, currently the most generalized procedure that we have discussed. And this procedure can be used to test one predictor. It can be used to test all predictors. So what I'm going to do is I'm going to confirm that we did in the previous class. I think we tested the significance of example 3.1. We tested the significance of X2, I think. So what I'm going to do is I'm going to replicate the same thing, but with partial F test. So I'm going to use the same delivery time data set. In this delivery time data set, we fitted the model, and I think we tested the significance of X2 somewhere. This one. Is it X2 or X1? Which? This t-test is for what? This is L17. Yeah, this is X2. We tested the significance of X2, and the corresponding p-value was what? 0.000631. What I'm going to do is I'm going to get exactly the same p-value, but with this procedure, the partial F test. Now see what I do. I have 2 predictors, by the way, in the model. Now, this is my full model. Clear? Clear? I want to test the marginal contribution of this portion of the model. This portion can be 1 predictor, 2 predictors, 4 predictors, 10 predictors, all predictor. Some predictors. So let's say I want to test this portion of the model. What I will do is I will fit a revised model without this portion of the model. So I'll fit another model. This is called full model. I will fit a revised model without this portion of the model. Clear? Clear? Now what I'm going to do is I will write the statistic in front of you here. I'm going to obtain some things from the first model and some things from the second model, and I will plug them into this F6. I plug everything into that model. Now, what do I need? From the full model, I need SSR and I need MSE. So I'll take these two quantities from the full model. From the revised model, I need what? I need just SSR. So I'll fit the two models and I'll get these three quantities from the two models. Now see how do we perform the complete analysis, the regression analysis with one click in Excel. Yes. Which is no one, not one parameter, say one predictor. You can use, yes. We used it actually in the class before, previous class, we used t-test for testing one predictor. Partial F-test is used for testing the part of the model. That part of the model can be one predictor. It can be. This is the general test. Now, look closely onto the screen. When you open Excel, in your data tab, you should have this data analysis option. If you don't have this option, this is what you have to do. You have to go to File and you have to click the options here. At the bottom of Excel options, you will see this options. In this options, when you open it, you will see add-ins on the left side. Click on this add-ins. Click on this add-ins and click OK. This will show you all the add-ins in your Excel installed currently. What did I do? Now click Go here. Is it? Yeah, this will show you all the add-ins that are available in Excel. So you will see here the analysis tool pack will be unchecked for you. If it is not appearing, this analysis tool pack will be unchecked for you. Check it and press OK. It will take 3 or 4 seconds and it will bring it here in the tab of data here. Now let me show you if it is not there, how this will look like. I will get rid of this one first and then I will bring it back. You see, it's not available now. On my data tab, it's not available. So what you need to do is you need to go to File, Options, Add-ins, go and check the analysis tool pack. Click OK, and it will come down here. Once it is here, now you need to do what? Now you need your data. So I don't want to create mess in this sheet. I'll take my data to another sheet and I will get rid of this ones column. I don't need it anymore. You can keep it if you want. Go to data analysis and and try to find the regression part here. You will see regression and you click OK. Now here you have to give the input variable, which is y. So give the overall range of y. I'm giving the range of y, including the title. Y is my predictor missing here. Where is x2? Oh, I did not copy x2. Copy and. So I'll go to data analysis, regression, and give the input y. And I'm giving the input y, including the title also. And I will check this option that I'm selecting the labels also. If you're not selecting the labels, don't check this option. And in input X, I will select the 2 columns. Now the restriction here is that the columns you are giving as the predictors, they should be together. So if I want to put X1 and X5 and X7 into the model, X1, X5, X7 should be together. Otherwise, Excel will not take the input. If the columns are not together, Excel will not take it. Suppose I have 10 predictors, the data on 10 predictors. There is X1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I want to fit the model of Y on X1, X7, and X9. So what I need to do first is I need to bring 1, 7, and 9 together. Before performing the analysis, I need to bring them together. Once they are together, Excel will only take that. So I give the data in column C and D as X's. And the things you see, the residual plots, this is your chapter 4. Normal probability plot is chapter 4. Output, I will take the output somewhere here in the same sheet, let's say here. And for the output, I click F2. So it will give the output around F2. And I press OK. This is your full model. From the full model, what do I need? Look at the formula. What do I need? I need SSR, which is sum of squares of regression. Yeah, this one, 5550.81. This is SSR of the full model. And what else do I need? MSE 10.62. This is MSE. These are the 2 quantities I need from the full model. Without any hard work, they printed this for you. You just take them from the output. Now I need to fit another model. Which other model? The model after deleting X1. So I'll fit another model. Go to the same data analysis option, regression, and this time I will change my X to only X2. Sorry. Yes. No, anything. You are not required to do it manually. You are not forced to do anything manually, unless I force you from the question. You see, I'll give you the question and I'll ask you to give me X prime X, not beta. So this time I give the output, let's say here in F23. So the second output of the revised model will appear in F23. So here is my F23 with only one predictor. This time my SSR is 5382. Now I have all the quantities complete. I just have to plug everything into. So let me write here. My SSR of full, that came out to be equals, it was 5550 point something, correct? My SSR of revised model, that came out to be 5380, correct? My MSE of full model came out to be 10 point something, correct? Now I'll just simply write the formula for partial F, which is what? Formula. SSR of full, this quantity, minus R of revised, this quantity, divided by how many restrictions? One predictor I'm testing in H0. 1, and I'll put another bracket around it, over MSE of full model. What is the value? 15 point something. This is the value of F. Now I have the option to use the rejection region approach, or I can use the p-value. if I find the p-value, what answer do I expect? I expect this exact answer that we got 2 classes ago, because the objective is same. In this, I'm testing the significance of beta 2 using the t-test 2 classes ago. I got 0.000631. Again, today I'm doing what? I'm testing the same, the significance of beta 2. So I'm gonna get the same, exact same p-value. So what is the p-value expression? It's the probability in F distribution more than this 15.85. So I'll go inside the F distribution. Why am I writing F dot distribution and not F dot inverse? I need probability and not the value. So I need probability. I will write F dot distribution. Probability more than what? More than this 15 point something, but it will not give me more than, it will give me less than. What should I do? Final answer, I will do 1 minus. So I'll do it later. Degree of freedom for the numerator, R. What is R? 1. Degree of freedom for the denominator, n minus k minus 1. N is 25. The k for full model was 2. 25 minus 2 is 23. Minus 1 is 22. So 22 degrees of freedom. Cumulative, always true. And finally, I'll do 1 minus to get the upper tail. What do I get? Same p value. No. It's whatever you used inside MSE. N minus k minus 1. This is called partial F test. Yes.
The contribution of x1 in the presence of x2 is about 200.
It's I can find it. Give me a second. It's this minus this. It is 168.
Can we say that the rest is the contribution of x2?
And x1, you mean?
We are testing for x1 or x2?
We're testing for x2.
Okay. Can we say that the rest is the contribution of x1?
It's not like this. Basically, let me give you an example. If there is no exam throughout the semester and end of the semester, I come to you and I tell you that you got A+, will you be happy? No exams, no scores, no feedback. I just tell you that you got the highest grade. You'll be happy. True? What contributes to your happiness? The grade. True? Now, then another situation, I come to you and I tell you that you got 97 out of 100. Will this contribute to your happiness in another situation? Yes, true. Now, if I tell you that you got 97 out of 100 and then I tell you you got A+, will you be the happiness, the increase in the happiness will be the same without telling you the prior knowledge of 97? No. If you already know that I have 97 out of 100 and then I tell you you got A+, you will not be happy as much. You will be happy, but not as much, right? And if I tell you straight away you got A+, you'll be much more happier. Now, what is contributing to your happiness? Some part is contributed by 97. Some part is contributed by A+, and some part is contributed by the interaction of the two, which we call the intersection. Clear? Now, this 5550 is a result of marginal contribution of x1, marginal contribution of x2, and the joint contribution of x1 and x2. Now, you cannot say that the remaining whole is the contribution of x1. No, it's basically this 168. If you subtract the contribution of x1 and the interaction part also, this is the contribution that is only brought by x2. So it's like this one. If I go diagrammatically, it is in explaining why this is the contribution of x1 and this is the contribution of x2. And this basically is explained by both of them. And we are interested in this part. The contribution of only x2.
Like the interaction terms, and you get the X1 contribution.
If you do the exact opposite, you fit the full model and then you delete x1 instead of x2 and you get the marginal contribution of x2, it will not be this. It will not be this. It will be less than this, because inside this there is also that interaction part. The question is, yes, we can, yes. The critical value F critical will be F dot inverse. What is the lower tail probability? The upper tail should be alpha. The lower tail should be what? 1 minus, let's say alpha is 0.05. Degree of freedom for the numerator 1, for the denominator 22. The critical value is 4.30095 for alpha 5%. So you will say because 15.85 is greater than this 4 point something, we choose to reject H0. Is this a coincidence that the p-values are same? It is not. It is, we'll not go into mathematical proof, but for testing a single coefficient, it is proved mathematically that this F statistic is nothing but the square of that t. You can confirm the value we got for t was 3.98 something, is it? Square it, you will get 15 point something, what we got for F. So we'll not do mathematical proof, but basically for testing single predictor, if you take the square of the t, it becomes F. Without going into the proof. Now, my question here is, can I use this procedure for testing the full model?
Yes.
Why not? In that case, I'll be testing H0, that beta 1 and beta 2 are both 0. True? Against H1. Correct? Now I need to fit two models, yes? Not equal to 0. Now I need to fit two models. One including the predictors, one excluding these predictors. So the full model will be what? And the revised model will be what? If I delete x1, x2 both from the model, I'm left with what? No predictor into the model, right? When I have no predictor into the model, how much variation will be explained? 0. No variation will be explained because you don't have a predictor into the model. True? And how much variation will be explained by full model? It is the full model. So what will happen to the partial F statistic? It is SSR of the full model minus 0 over R divided by MSE. Correct? Correct? What is R? In this example, it's K. I'm testing all predictors. True? So it will become SSR over K over MSE, same as that F statistic in the red color. Right? So this procedure can be used, I showed it can be used for one predictor, can be used for all predictor, can be used for some predictors. Just a little example. Suppose I want to fit this model. And in this model, I want to test the marginal contribution of beta 1 and beta 4. Which two models do I fit? Whole model, correct? What should be the revised model? What should be the revised model? 2, 3, 5. Right? I will get SSR full from here, and I will get MSE from here, and I will get SSR revised from here. What will be R? Now tell me, will it be this 3 or this 2? 2. Full. Is it clear? We discussed how to test the significance of a single predictor. We discussed how to test the significance of some predictors. We discussed how to test the significance of all predictors. But none of these procedures will allow you to test this. What if you want to test that beta 1 plus 4 beta 4 is 9? A linear constraint onto the model. What if you want to test this? Before that, the question comes, why do you want to test this? The answer is, if this is really true and this is authentic information, but beta 1 is nothing but beta 4, instead of beta 1, you can put 9 minus 4 beta 4 into the model, and you can work with one less unknown parameter. If this information is authentic and correct, you can reduce the number of parameters in the model. That will increase your degree of freedom. So your model will be more efficient. The confidence intervals will be less wider. You need to prove it before using it. You need to prove it. You need to test it. Yes. Now the question is, does any of the procedure we discussed allow you to test this thing? No. None of the procedures allow you to test this one. To test this one, or let's say I want to test that this is this, and beta 2 minus 4 beta 9 is minus 1 against H1, that at least one constraint from H0 is not true. I can ask you to test as many constraints as I want into a single hypothesis. I can give you 7 equations. None of the procedures will allow us to test this thing. To test this thing, we have a generalized F-test, which we will discuss in the next class. Major will be up to this line, this line. If you have any question from today's class, you can ask, otherwise you can leave. And those who were using and who are using mobile in the class, see me.
Thank you.